Uh, yeah, Rachel, please start.
Okay. All right. Well, thanks everyone for joining. Today I'll be talking about the 50 most appeared keywords for deep learning in 2023. I'm going to go in depth with the first 10, but I'll go over briefly of the 50, the the 50 of them. Yeah. So, for those of you who don't know me, my name is Rachael Phillips. I'm a senior consultant at Microsoft. I work in the data and AI realm of the world, well, of the organization, which is its own organization inside of Microsoft. So it's pretty obviously, we all know Microsoft's huge. So I'm a very small fish in a very big pond, very big pond. But yeah, so this is my information, my personal work and emails, and then my webpage. So ICLR 2023 open review data. These are the top 50. I'm not going to read them all out. You obviously will be able to look at them on your own. But I'll read the first 10. But reinforcement learning, deep learning, representation learning, graph neural network, transformer, federate learning, self-supervised learning, contrastive learning, robustness, and general model. This was actually really cool to go in depth on a few of them because I didn't know what all of these were myself. So it was kind of a neat experiment. So with that being said, this next 5 slides are just basic short definitions of the 50 keywords. So I'll go over them briefly. And this was actually because Lev did this next five slides for me. But 1 second, I'm going to move this. Okay. So the first 10, reinforcement learning. So this is a type of machine learning where an agent learns to behave in an environment by performing actions and seeing the results. So it's just reinforcing. And deep learning, we all know is well, actually, maybe we don't all know, but it is a subfield of machine learning that uses neural networks with many layers. So that's why it's called deep learning. It learns representations and performs tasks, often outperforming traditional machine learning approaches because of that extra deep layer underneath. Representation learning. This involves training a model to automatically discover the representations needed for data analysis or task performance. Graph neural networks that are specifically designed to operate over data structured as graphs. A transformer. Transformer is a type of deep learning model introduced in the Attention is All You Need paper, used widely for tasks like language translation and text generation. Federated learning, a machine learning approach where the model is trained across many decentralized devices or servers holding local data samples without exchanging the data samples themselves. Self-supervised learning it's a very similar, it's an unsupervised learning method where the data provides the supervision. In other words, it's a type of machine learning where the data set both trains and labels itself. So of course, we know unsupervised learning is where, you don't actually have any sort of output. So it's not something you know the answer to. So that's cool that that self-supervised can do that. Contrastive learning is a technique for learning representations by enforcing that similar instances are close in the learned representation space, while dissimilar ones are further apart. So it's kind of similar to clustering in a way. I think there's more layers to it, though. Robustness is the ability of a machine learning model to deliver consistent results despite changes in the input data or minor alterations in the model's architecture. And generative model is a type of machine learning model that is capable of generating new examples that resemble the training data. The next 10 are continual learning, also known as lifelong learning. This refers to a system's ability to continually learn over time by accommodating new knowledge while retaining previously learned experiences. So it's continuously learning, which makes sense. Neural network, a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. Transfer learning is the process of training a pre-trained model on a new data set, leveraging the learned features of the original model to improve learning efficiency and performance. A diffusion model is a type of generated model that simulates a random process, often used to generate realistic images, sounds, and other data samples. That one's cool. Generalization, the capability of a machine learning model to perform well on unseen data after being trained on a limited amount of data. A language model is a type of natural language processing, which makes sense, that predicts the likelihood of a sequence of words appearing in a given language. Computer vision, interdisciplinary scientific field that deals with how computers can gain high level understanding from digital images or videos. Knowledge distillation, a process where a larger, more complex model, a teacher, trains a smaller, simpler model, or a student is what it's called, is replicate its behavior. Vision transformer. This is a transformer-based model architecture used for computer vision tasks, showing strong performance by leveraging the self-attention mechanism across image patches. Offline reinforcement learning, a method of reinforcement learning that utilizes a pre-existing data set without additional online data collection, also known as batch reinforcement learning. So I'm not going to go over the rest of them. I feel like this is a little redundant, but you can go and look at these in more depth. But what I want to go and focus on is the top 10. So the top 10, I used ChatGPT to give a more in-depth description. And then also I have a little bit of history and some extra information about each one. So reinforcement learning. Reinforcement learning is a machine learning paradigm where an agent learns to make decisions by interacting with an environment to maximize cumulative rewards. So you can see how the reinforcement learning happens here, where you have your environment and your agent, and you have a reward that then the agent takes an action on and goes back to the environment. So it's reinforcing that that information. So through trial and error, the agent explores the environment and learns from its actions consequences. The actions consequences. So key components include the agent, the environment, the state, the action, and the reward. RL algorithms include value-based methods, so things such as Q-learning or SARSA, policy-based methods such as reinforced proximal policy optimization, and actor-critic methods such as advantage actor-critic, deep deterministic policy gradient. RL has been applied to robotics, game playing, recommendation systems, autonomous vehicles, and more. So reinforcement learning, this is a little bit of history on it. The origins of RL are in animal behavior. It actually dates back to the 1930s. This psychologist, his name was B.F. Skinner. He was doing the animal testing and that reinforcement learning. So the idea that an animal or an agent could learn from past experiences. I don't remember exactly. I think it was like rats or something, and he was having them do some different tests and had some hypotheses and confirmed that, yes, they learn from their past experiences. So, of course, this entered the world of computers later on. And in the 1950s and 60s, Richard Bellman over here created the Bellman equations. They were a set of nonlinear equations that once solved provide that once solved provide an agent with an optimal policy. So that is, once the Bellman equations are solved, an RL agent can act optimally in its environment. So whatever that happens to be, a maze, a racetrack, or a stock market, etc. So it was so even further along, it was further developed by Samuel and Sutton. This guy, Dmitry Bertskis, I'm not sure if I'm saying that right. He was also in there. I didn't actually write him down, but he teaches this stuff at I can't remember what school, but one of the universities. And he also had a lot to do with the reinforcement learning history. And then Richard Sutton's right here. But they gained mainstream exposure in the 80s and the 90s with the publication of influential papers by RL pioneers. I didn't put all of these guys on here, but Kalbling, Littman, and other RL researchers. Since then, RL has been successfully applied to a wide range of problems, which I mentioned before: gaming, robotics, and so on and so forth. In this slide, you can also click on the article that I found a lot of this information from, or all of the information actually. So the second word was deep learning. So deep learning is a subfield of machine learning, which focuses on deep neural networks that learn complex patterns from large data sets. It excels in tasks like image recognition, which is, I think, one of the biggest examples that everybody uses with deep learning is image recognition, being able to decide if a dog is a dog or a cat is a cat. That's, of course, a very simplistic example, but you get the idea. It's also been used in natural language processing, speech recognition, and reinforcement learning, which we were just talking about. Deep neural networks consist of multiple layers of interconnected nodes processing data in a hierarchical manner. Popular DL architectures include convolution neural networks for image recognition, recurrent neural networks for sequential data, long short-term memory, and gated recurrent units as RNN, which is the recurrent neural networks variants, and transformers from natural language processing tasks. DL's our popularity stems from large data sets, hardware advances, and improved training techniques, but faces challenges like the need for labeled data, computational resources, and model interpretability. So as you can see, deep neural networks have quite a bit of layers to them, and they're very complicated networks. So here's a little bit of history on deep learning. So the earliest efforts in developing deep learning algorithms came from Alexei. I am not going to be able to say his name. If anyone knows how to pronounce it, you may speak now, but I don't.
Ivanenko.
Ivanenko? Okay, thanks. Thank you. He developed the group method of data handling, and Valentin Lapa, not sure if I'm saying that right either, is the author of cybernetics and forecasting techniques, both in 1965. So they used models with polynomial, complicated equations, activation functions that were then analyzed statistically. So from each layer, the best statistically chosen features were then forwarded onto the next layer. So it was a very slow and manual process at this time. The first convolution neural networks were used by another name I can't pronounce. He designed neural networks with multiple pooling and convolution layers. In 1979, he developed an artificial neural network called neocognitron, which used a hierarchical multi-layered design. In 1989, Jan LeCun provided the first practical demonstration of back propagation at Bell Labs. So I didn't put all the guys, but I put a little picture I found of Bell Labs. He combined convolution neural networks with back propagation onto like handwritten digits, which I think probably a lot of you have seen that before. I've seen it myself a few times in examples of deep learning. This system was eventually used to read the numbers of handwritten checks. So around the year 2000, the vanishing gradient problem appeared. It was discovered features or lessons formed in lower layers were not being learned by the upper layers because no learning signal reached these layers. So then they, of course, continued development. And in 2001, a research report by the Meta Group, which is now called Gartner, which we all probably have heard of them, described the challenges and opportunities of data growth as three-dimensional. The report described the increasing volume of data and the increasing speed of data as increasing the range of data sources and types. This was a call to prepare for the onslaught of big data, which was just starting. So jump ahead 8 more years, and 2009, Fei Li, an AI professor at Stanford, launched ImageNet, assembled a free database of more than 14 million labeled images. So by 2011, the speed of GPUs had increased like significantly, making it possible to train convolution neural networks without the layer by layer pre-training. So with that, it increased the computing speed, and it became obvious that deep learning had significant advantages in terms of efficiency and speed. So one example of that is AlexNet, a convolution neural network whose architecture won several international competitions between 2011 and 2012. And then from there, 2012, Google Brain released the results of an unusual project known as the CAT experiment, the free-spirited project exploring the difficulties of unsupervised learning. Deep learning uses supervised learning, meaning the convolution neural net is trained using labeled data. So yeah, so there's a little bit more to it, but ImageNet was a big one, so I put them on here as well. But there's been a lot of work done by a lot of these brilliant people. So the next one of the top 10 is representation learning. Representation learning, I've briefly mentioned, is a subfield of machine learning, which focuses on automatically learning useful features from raw data for tasks like classification, regression, or clustering. It aims to discover meaningful data structures and create compact representations, replacing manual feature engineering. Deep learning, a form of representation learning, uses deep neural networks to learn increasingly complex features as data passes through layers. Other techniques include autoencoders, word embeddings, variational autoencoders, and generative adversarial networks. Representation learning has improved applications in computer vision, natural language processing, speech recognition, and bioinformatics by automating feature extraction. So it's kind of interesting because, as you can probably notice, which, these are all very similar topics, and there's a lot of overlap with them. But anyway, so but it's kind of cool. So instance grasping, they're looking for what's the goal, what's the outcome, and it generates labels. before, after outcome, and then it just continuously does that. All right, so number 4, graph neural network. So obviously a graph neural network is a network that is using a graph structured uh, to handle graph structured data, such as social networks, biological networks, or knowledge graphs. These neural networks can capture complex relationships between nodes and edges, making them suitable for tasks like node classification, link prediction, and graph classification. Excuse me. They also consist of layers that perform message passing between neighboring nodes, aggregating and updating node features iteratively to capture local and global graph structures. Key GNN variants include graph convolutional networks, graph sage, and graph attention networks, or GATs. GNNs have shown success in diverse domains, including recommendation systems, drug discovery, and natural language processing. So, initial representation of each node, the GNN then looks at the output representation of each node. So, yeah. Graph neural network history. So, since 2006, graph theory has come in close contact with machine learning with the new concept of graph neural networks. The very first proposal was published in 2006 by Scarcelli and Gorey, and subsequently generalized in 2008 with the paper, The Graph Neural Network Model. Here, the authors laid the mathematical foundations for the modern graph neural network. Since then, the literature has seen spikes in graph ML works, which made the graph world evolve more and more, defining more precisely what are the key elements of these mathematical structures and how to link them with more refined machine learning algorithms. And there's a couple articles I found about it there. So next one we're going to talk about is transformers. Transformers are a class of deep learning models that have revolutionized natural language processing tasks. Transformers were introduced in the paper Attention is All You Need by Vaswani et al. Transformers employ self-attention mechanisms to process input sequences, efficiently capturing long-range dependencies without relying on recurrent structures like RNNs. Key components include multi-head self-attention, positional encoding, and layer normalization. Transformers are highly parallelizable, making them suitable for large-scale training on GPUs. Oh, that's good. Uh, models like BERT, GPT, and T5 have achieved state-of-the-art results in various NLP tasks, including machine translation, text summarization, and sentiment analysis. In a nutshell, the task of the encoder on the left hand of the transformer architecture, so this side, is to map an input sequence to a sequence of continuous representations, which is then fed into a decoder. The decoder on the right hand of this architecture receives the output of the encoder together with the decoder output at the previous time step to generate an output sequence. And this image came from this article, and then there's more history on the transformer found here. Number 6, federated learning. Federated learning is a distributed machine learning approach that enables model training on decentralized data, typically spread across multiple devices or institutions. Instead of aggregating raw data in a central location, federated learning trains local models on each device and shares only the model updates, which are then aggregated and used to update the global model. So these are all the different local models, and then this is the global model that uses all the local models. This process maintains data privacy as sensitive information never leaves the devices. Federated learning is particularly useful for scenarios with privacy concerns like healthcare or finance, and for edge devices such as smartphones or IoT sensors. Federated learning addresses data security, privacy, and regulatory compliance while enabling collaborative learning. So the term federated learning was coined by Google in a paper first published in 2016. And since then, it has been an area of active research as evidenced by papers published on ArcSiv. I don't know if I'm saying that right, but in the recent TensorFlow Dev Summit, Google unveiled TensorFlow Federated, making it more accessible to users of its popular deep learning framework. Meanwhile, for PyTorch users, the open source community OpenMind had already made available the PySift library since the end of last year with a similar goal. So these are some of the links and then you can also find the papers here on these links as well. Self-supervised learning. So self-supervised learning is a machine learning approach that leverages unlabeled data to learn useful features or representations. It uses the structure within the data to create artificial tasks where the model generates its own labels or targets, bypassing the need for human annotated labels. So self-supervised learning can be considered a form of unsupervised learning with an added supervisory signal. Common techniques include contrastive learning, denoising autoencoders, and masked language modeling. Self-supervised learning has shown promise in domains like computer vision and natural language processing, reduce the reliance on labeled data, accelerating pre-training, and improving performance when fine-tuned on smaller labeled data sets. So I didn't go over much of the history here, but there's some links in here that have some information on it. But yeah, so it's kind of a similar like classification or regression, where it's unsupervised, but it has that extra layer of supervisory signals. Contrastive learning. Contrastive learning is a self-supervised. So this is a type of that self-supervised learning, which also I said in the last slide. But it's an approach that learns to distinguish between similar and dissimilar data points by comparing pairs or groups of samples. So to me, this seems a lot like kind of clustering in a way, or something, similar. But in this method, positive pairs consist of different views of augmentations of the same data point, while negative pairs comprise unrelated data points. The objective is to learn a representation that brings positive pairs closer and pushes negative pairs apart in the embedding space. Contrastive learning has gained prominence in computer vision, with methods like SIM-CLR and MoCo achieving strong results. It has also shown promise in natural language processing and other domains, reducing the need for labeled data. Robustness. This term is in machine learning. refers to the resilience and stability of a model when it's exposed to various types of input data, including noisy, incomplete, or adversarial examples. So, a robust model maintains its performance and accuracy under diverse conditions, generalizes well to new, unseen data, and is less prone to overfitting. Ensuring robustness is crucial for real world applications where data quality and distribution may vary. This is achieved through techniques such as data augmentation, regularization, adversarial training, and ensemble learning, which together help create models that can reliably, and effectively handle uncertainty in diverse scenarios. So there's an example of robust and non-robust, and then below are some links on robustness that will give you more details about it. All right, so number 10 is generative model. A generative model is a type of machine learning model that learns to generate new data samples resembling the training data. So it captures the underlying structure and statistical patterns in the data, allowing it to create plausible synthetic examples. Generative models are widely used in various applications such as image synthesis, text generation, and drug discovery. So, two popular types of generative models are variational autoencoders and generative adversarial networks. So, VAEs leverage probabilistic graphical models and optimize latent variable representations, while GANs employ a two-player game between a generator and a discriminator to produce realistic data samples. So GANs, tend to be more widely used for generating multimedia, while VAEs see more use in signal analysis. Ian Goodfellow and fellow researchers at the University of Montreal introduced GANs in 2014. They have shown tremendous promise in generating many types of realistic data. Jan LeCun, which was mentioned in a previous slide, chief AI scientist at Meta, has written that GANs and their variations are the most interesting idea in the last 10 years in machine learning. And then there's a couple links at the bottom for more information. Oh, there's more. There's another page. I forgot about this page. GANs tend to be more widely used for generating multimedia, while VAEs see more use in signal analysis. So Ian Goodfellow, he's down here on the bottom left, and fellow researchers at the University of Montreal. Oh, okay. I accidentally put that twice. Anyway, so I'll skip to the next part. For starters, GANs have been used to generate realistic speech, including matching voices and lip movements to produce better translations. They have also translated imagery, differentiated between night and day, and delineated dance moves between bodies. Combined with other AI techniques, they improve security and build better AI classifiers. So VAEs, of course, like I said, they were introduced in 2014, but this guy, Deirdrick Kingman, a research scientist at Google, and Max Welling, to his right, research chair in machine learning at the University of Amsterdam. VAEs also promise to create more effective classification engines for various tasks with different mechanics. At their core, they build on neural network autoencoders made up of two neural networks, an encoder and a decoder, which we actually saw a visualization of that earlier. The encoder network optimizes for more efficient ways of representing data, while the decoder network optimizes for more efficient ways to regenerating the original data set. And this is where I got most of my information. So that's that link. And that's it. Any questions, comments?
Well, Rachel, first of all, thank you. There's a lot of information.
Yeah, sorry. That was it was like just a spam of information.
Yeah, I want to mention something about Fukushima and his neocognitron, because it was convolutional network predated Jan LeCun's work by like 10 years. And Jan LeCun knew about neocognitron. And so he's an amazing guy. He's still alive. He's something like 86 years old.
Oh, that's cool.
Yeah, he's in Japan, and he created the network, but back then he didn't know, like, the method of backpropagation was not. I mean, mathematics exists, but it was not like recognized yet, so he didn't use it. But anyway, just he's amazing character, and I recommend, like, if you like history, to look him up. Another thing about variational autoencoders and GANs, so both use randomness, right, internally, but kind of differently. And both achieve very good results. In my head, I always compare, like, in evolutionary sense, you may have an organism with only one sex, like no sex, or you may have organism with two sexes, and then they can exchange genetic material, and then evolution goes much faster and training goes much faster. So GANs, it's kind of similar, and because you have two players, right? The creator and discriminator, and it's just so many applications, and it improves the training. It achieves unbelievable results. So every time when you have a model, you can immediately think, what if I'll add sex to it? What if I'll, instead of one network, we'll use two networks, and like, see how it will work. Yeah, but here's some amazing ideas. The graph networks, if you just think, so, okay, you have a graph. So let's say you have people, and they have connections, preferences, and whatever, and each preference may be one row of your data. So you can learn one graph, which, let's say, it consists of people, and then you can ask questions like, okay, I have this person, find me similar people and find me what preferences they have, and you can build recommendation engine from this or other tasks. Well, commonly in what we do with regular clients, they don't use graph networks, but it's a very, very interesting area, and very, like, powerful. About representation, if you go to the very beginning, so when it started, ICLR, this is a conference on representations. So how you find a compact way to learn the representation of your data, which will be compact and at the same time useful and expressive, right? So it's actually the essence of machine learning. And this is a very famous conference, of course. And yeah, it's like the third one, like reinforcement, deep, and then representation learning. It's not by accident, because this is really the core thing which people do in machine learning. They try to find a good representation of your data, a simple representation. Like, even if you go to a simple regression, draw the line through the points, and then the presentation will be ax plus b, it's a line, right? This is the compact, simple representation of your data. Self-supervised learning. This is really a great idea, right? So let's say you have very few pieces of data. Let's say you have 10 images. So you can take an image, and then you can make it wider or like taller or whatever. You can rotate it, you can squeeze it, you can mirror it, you can distort it in many different ways, and you can produce 1,000 images from this one image. And then you use this data to train your network, right? Because usually the first layers of the network, they just learn to find lines or edges or angles or whatever. So you can basically train like the first several layers using this simple approach of generating your own data. And then after that, you can actually train it on whatever real data you have. So yeah, this is very powerful. I remember Jan LeCun was thinking how excited he was about finding this approach, because if you have more data, you can make your model better, right? And this is kind of similar to what people do, let's say DeepMind or Tesla, when they're training their powerful models. They make these models train with itself, against itself, in virtual world, right? So they add some randomness to generate more and more situations. And yeah, so it's kind of similar to self-supervised learning. Well, in idea, right? You generate, you self-generate data to make your model better and better and better. Like AlphaGo was playing with itself. That's how it became better than humans, right? Transformer. Oh, about transformer, because this is like everything now is a transformer, right? And the idea started with a simple translation. You translate word into word, right? But then people realized, well, same word in different places, in different context is different. So we have to think about context. What if we will define the word by the words around this word? And we go to the word-to-vec model, where the meaning of the word is described by its local neighbors, right? And it worked, but well, what if this neighbor, you should include neighbors which are not like close to the word? And then, well, how you find what are the most important words and what are the most important connections? And that's what attention mechanism does. It tries to figure out on which word in a sentence to put attention, right? And you have encoder and decoder with these attention mechanisms to select the most important pieces properly and to weigh them and then to normalize and then repeat the process again. And this is the transformer. The idea is very simple. Implementation is, well, not so simple to understand looking at the graph. But it's amazing because the same logic, how you find important representations, important pieces, how you focus your attention, it applied to text, to images, to everything, right? And now we have GPT, which is what? Generative, pre-trained transformer. And as they were perfecting their transform architectures and made BERT, which is idea is bidirectional and it can be pre-trained. So, so much progress in the last 6-7 years. It's just Rachel, thank you.
Yeah, thank you guys for listening. I know it was a lot.
Rachel, thank you very much. It's very interesting.
Yeah, it is.
As usual, but it's really, it's a complicated subject, but very well presented. I don't know. Thank you so much.
Thank you.
Okay. I'll stop recording.